All right, in the last video, we talked about the law of inertia and the conservation of momentum. Now we're going to continue with the conservation of momentum, but in this video, we're going to talk about inelastic collisions and the coefficient of restitution. So we already saw this slide in the last video, but I just want to remind us that linear momentum is the product of an object's mass and its linear velocity. And that's the equation here. So remember that momentum is capital L. And the faster an object moves, the more momentum it has. And the larger an object's mass, the more momentum it has. Okay, so far we've only talked about perfectly elastic collisions, but not all collisions are perfectly elastic where the momentum and the kinetic energy are conserved through the collision. So remember that in the last video, we saw these marbles hitting each other. They were just bouncing off of each other. That's an elastic collision. That's what an elastic collision refers to, is objects just bouncing off of each other. Now, the opposite of a perfectly elastic collision is a perfectly inelastic collision. So in a perfectly inelastic collision, momentum is still conserved, but rather than bouncing off of each other, the objects in the collision stay together after the collision and they move together with the same sort of post-collision velocity. For an inelastic collision, we still start with this general conservation of momentum equation for both the colliding objects. So remember, 1 and 2 just shows you two different objects. But we know that in an inelastic collision, the post-collision velocity of object 1 will be the same as the post-collision velocity of object 2. So in an inelastic collision, we can refer to the post-collision velocity just as v for the final velocity. So that means that that general equation can be simplified to this equation down here for an inelastic collision. So most of the tackles that happen in football are examples of inelastic collisions. In most of these collisions, the two colliding players move together as one sort of unit or system following the collision, if it's a successful tackle. Football puts a premium on momentum. Mass and velocity are equally important. So fast and large players are the most successful players. This is me saying that from a non-football perspective, purely a biomechanics and momentum perspective. So let's try a problem to sort of highlight the mechanics of an inelastic collision. Again with football. So let's pretend that there's an 80-kilogram running back, so this guy here, that collides with a 120-kilogram linebacker. Just before the collision, the running back has a velocity of 6 meters per second towards the goal line, so towards this goal line over here. And this linebacker has a velocity of 5 meters per second in the opposite direction. If the collision was perfectly inelastic, meaning that they collided and stuck together, would the running back be moving forward and score a touchdown just after the collision, or would the defense prevail? So I've highlighted all the information that I just said here. This is all you need. I invite you to pause the video now and try to work through the math and answer that question. Would the running back or the system really be moving forward towards the goal line and score a touchdown after the collision, or would they be moving in the opposite direction because the defense prevailed? That's what we're trying to figure out here. So hopefully you've taken some time to try to work through that on your own. Let's solve the problem together now. So we're told that the collision is perfectly inelastic. So we use the equation for a perfectly inelastic collision where the post-collision velocity is the same for both objects, or in this case, both football players. So next we substitute our known variables into the equation. And I decided that towards the goal line was positive. So the running back was moving 6 meters per second towards the goal line. And then the linebacker was moving 5 meters per second in the opposite direction. So that's why there's a negative there. And what we're trying to figure out is this post-collision velocity here. So thankfully, that's our only unknown. We're able to solve the problem, and we end up with a post-collision velocity of negative 0.6 meters per second. Now, what does this number mean? If we go back to the problem, the question was, will the running back score or will the linebacker prevail? What's your answer? What's our answer? The running back will not score because he and the linebacker are moving in the negative direction after the collision. So they're moving away from the goal line with a velocity of 0.6 meters per second. Nice. Unfortunately, most collisions in sports and in real life are not perfectly elastic nor perfectly inelastic. They're somewhere in between the two. They're still called elastic collisions. They're just not perfectly elastic collisions. And the coefficient of restitution is a means of quantifying how elastic the collisions of objects are. So the coefficient of restitution, which is defined by the letter E here, it's defined as the absolute value of the ratio. So these sort of straight brackets here represent absolute value of the ratio of the velocity of separation to the velocity of approach. So let's define those two. The velocity of separation is the difference between the velocities of the two colliding objects just after the collision. So if you picture two objects hitting each other, the velocity of separation is that difference between their velocities just after they hit each other. So it describes how fast the objects are moving away from each other. The velocity of approach, on the other hand, is the difference between the velocities of the two colliding objects just before the collision. So it describes how fast the objects are moving towards each other. So this is the mathematical work through of the coefficient of restitution. So absolute value, right? The straight brackets, and it's a ratio, so it's a division of the velocity of separation post-collision divided by velocity of approach pre-collision. The coefficient of restitution has no units, just like radians, it's unitless. For perfectly elastic collisions, the coefficient of restitution is 1. That's the maximum value. And for perfectly inelastic collisions, where the objects just stick together, the coefficient of restitution is 0. That's the minimum value. And if we know the coefficient of restitution for the two objects in an elastic collision, then this, along with the conservation of momentum equation, that gives us the information that we need to determine the post-collision velocities of the colliding objects. The coefficient of restitution is affected by the nature of both objects in the collision. So for ball sports, it's most easily measured if the object that the ball collides with is fixed and immovable, something like the ground. Then only the pre- and post-collision velocities of the ball need to be measured. So actually, if the ball is dropped from a specified height onto this fixed impact surface like the ground, then the height of the rebound and the height of the drop provide enough information to figure out that coefficient of restitution. So this equation is derived from the elastic collision equation and the coefficient of restitution equation. The coefficient of restitution is a critical measure in most ball sports. For example, if baseball bats had higher coefficients of restitution with baseballs, then more home runs would be hit. If golf clubs had higher coefficients of restitution with golf balls, then longer drives would be easier. So obviously the rule makers regulate that coefficient of restitution for the balls and the implements that we use in sports. Most rules for ball sports directly specify what the coefficient of restitution has to be for the ball on the playing surface or the equipment that the players are using. So if we just do an example with this new equation here that we just talked about for the coefficient of restitution, the rules of racquetball state that the ball must bounce to a height of 68 to 72 inches if it's dropped from a height of 100 inches. So knowing this, we're trying to figure out what is the range of allowed values for the coefficient of restitution. Well, we have the rule being the bounce height has to be 68 to 72 inches. So that's our range. That's our lowest and our highest. And we're dividing that by the drop height of 100 inches. So we get a range of a coefficient of restitution between 0.82 and 0.85 for racquetball. Okay, there's this cool video that I want to show you. It's only 2 minutes, so bear with me. It's kind of funny, and it's about momentum.
Welcome to the Science of Stupid Christmas Grotto. And as you can see, we have spared literally no expense with the decorations. But what would really make my Christmas would be to wake up on the big day to a fresh dusting of snow. Nothing beats that gentle caress of snowflakes on your face. Yeah. In the right conditions, that soft, fluffy stuff that falls from the sky feels more like concrete. But what if we stick to rolling our snowballs? Much more pleasant, right? Okay, I think we'd better see some science. Roll a snowball down a hill, and it gains mass as it picks up snow, which compacts as it rolls, making it denser. The more mass or speed the snowball has, the more momentum it'll have. If the snowball hits someone, it'll transfer some momentum to them as it loses momentum. Sorry, but it's the law of conservation of momentum. Now, before we start rolling, there is something else you should know about density. Freshly fallen snow is soft and fluffy. But if it melts and refreezes, some of it turns to ice, which is just 8% less dense than water, and just as heavy, but rather more solid. So you've got a mitt full of snow, now for momentum. Find yourself a nice slope and roll away. But please, be careful. Believe it or not, rolling 1-ton snowballs can be very dangerous. See what I mean? More mass equals more momentum. Now, that one appears to have a lot less momentum, but it's increasing to about the same as a motorbike doing 22 miles an hour.
Okay, that was fun. That's it for this lecture video. We have one more lecture video for linear kinetics.